right. Today we have Dimitri Zagorulia from the Moscow Institute of Physics and Technology. Dimitri attended the SMA data analysis school in Hawaii recently and met some of our colleagues. And he is working on machine learning for morphological classification for radio data in AGNs. So I thought we haven't really had a whole lot of radio talks this semester. So we're gonna have one today. And if you do have questions, please wave your hands at some point and I will make sure that I interrupt Dimitri to take any questions. Dimitri, the floor is yours. Can you hear?
Yeah, I can hear.
All right.
Thank you. So, yeah, as Rafael introduced me, my name is Dimitri, or Dima for short. I know that Dimitri could be hard to pronounce, so Dimitri call me Dima. And I'm a first-year master student, and well, other than studying in Moscow Institute of Physics and Technology, I'm also a junior researcher at the Lebedev Physics Institute of Russian Academy of Science, and my scientific advisor is Mikhail Lysakov, which is currently in Chile working on VLBI. So I would like to present my talk today, the morphological classification of active galactic nuclei. And I cannot change my slides. Okay, now it works. So let's start with a brief astrophysical introduction. So as we all know, normal galaxies have a supermassive black hole located in the center of it. And about 1% of all normal galaxies, they have jets. And jets are relativistic plasma outflows that due to obviously relativistic effects are vividly defined on the images that we obtain. So normal galaxies could be divided into radio quiet and radio loud, and the latter ones were extensively studied by Fanaroff and Riley, and they distinguished two classes: Fanaroff-Riley 1, whose luminosity is decreasing with the increase of distance from the center of the galaxy, and Fanaroff-Riley 2, whose luminosity is increasing to the edge of the galaxy. So Fanaroff-Riley 1 on the left, Fanaroff-Riley 2 on the right. But and additionally, they found out that there is a correlation between the total luminosity and their morphological class, which is interesting. But those were kiloparsec scales. And nowadays, with the improvement of telescope resolution, we obtained parsec scale images. As we can see, the jet's direction could be different at different scales, which is actually really fascinating because we do not actually yet know why this could happen, but we have a hypothesis that probably a large gravitational influence could be the reason to this, probably something like a merge of supermassive black holes quite close. So a couple of words also about the method that is used to obtain these images of AGNs. It's the Very-Long-Baseline Interferometry, and it is as well normal interferometry. It is based on measuring the visibility function, also known as the spatial coherence, and taking the inverse Fourier transform from it to obtain the intensity distribution of the sky. But obviously, this problem is actually ill-posed because due to the fact that we only measure a couple of points, a couple of visibility functions, and the inverse transform will get us a lot of synthetic artifacts that are actually not in the real image. So, but however, a iterative clean algorithm was developed in the last century called CLEAN, and it produces a more or less clean map for this purpose. So it's actually quite good. Now about our research motivation. So besides the obvious astrophysical interest of researching active galactic nuclei, There is also other applications. For example, due to the fact that AGNs are located very far away from the Earth, their angular velocities could be neglected, and they're often used as reference points for Earth navigation. So additionally, having this morphological classification could help scientists to create different subsamples of and investigate objects with known morphological properties, and vice versa to investigate anomalous objects as well. So let's state our research problem. So we have a data set, the Astrogeo data set, that contains more than 130,000 of images for more than 20,000 objects. And we would like to classify it due to 4 morphological classes, which are the Gaussian source, the double Gaussian source, single-sided jet source, and the double-sided jet source. We picked these 4 as we thought that these are the 4 main, the easiest one to classify to. So that if anyone is wondering why we pick specifically these 4. And well, we have the first stage of our research obviously is working with data. So due to the fact that this is real data that was obtained from telescopes, it always has some outliers or noisy images. So here are some examples on the left of the noisy images. And we propose a criterion to filter these images. So we know that the telescope is pointing at the brightest pixel on the sky. So we assume that if the difference between the center of the map and the intensity, maximum of intensity, is more than 3 pixels, that there is something happen, that something happened in the observation, which makes it not normal, let's say like that. And additionally, we also added a signal to noise ratio criteria. So if it's lower than 10, we will assume that there is only noise and there is no signal. So this way, we eliminated 2.3% of images. So it actually seems to be that the Astrogeo dataset is actually quite clean and there's not much outliers there. And due to the fact that we have a lot of images that we cannot manually classify, it is appropriate to use machine learning techniques. So we introduce a quite simple convolutional neural network that consists of 5 convolutional layers and 2 fully connected layers to classify these objects. So 0 would be the probability it to be for the Gaussian source, 1 for the double Gaussian, 2 for the single-sided jet, and 3 for the double-sided jet. But convolutional neural network works only, it is a supervised learning technique. So it assumes that there is some sort of training data set that is already labeled. To fix this, we proposed additionally a synthetic data. So the first row is the model sources. They're essentially drawn by me by hand. So this is the Gaussian source, double Gaussian source, single-sided jet source, and double-sided jet source. Well, we also obviously augmented them. We moved them around. We changed some parameters of them. After that, we convolved these model sources with a point spread function. These point spread functions were obtained through a clusterization of parameters of the initial Astrogeo dataset. And after this convolution, we get the second row. And we can see and compare it to the third row, which is actually the real sources. It is not only visually similar, but also statistically. We also checked the histograms of intensity, and overall it looks fine. So we used these synthetic data and synthetic images as our training data set for our CNN. So we train our CNN, and this is the confusion matrix that we got for our test data. Well, we split our synthetic data on train and test as we usually do. So, and this is the results. So obviously our model was trained quite well and it predicted good enough on the test data. And we used our trained data, not trained data, but the trained model to predict on real images. So this is the histogram that we get, well, essentially inferencing our model on real data. So we get most of them, most of the images were predicted as Gaussian sources or point-like sources. And this actually is what we would like, what we expect, because Astrogeo dataset was initially constructed for astrometric purposes, so they would probably pick AGNs that don't have any spatial structure, some like jets. But the problem is that we cannot actually quantify these results, because the problem itself is to get labeled images, to classify them. So this is some examples that we looked through of our predictions. So on these images, it works actually quite well. So the first row is the Gaussian sources. The second row is the double Gaussian sources. Then we have the single-sided jet sources and double-sided jet sources. So it seems to be that model is, at least on the first glance, is more or less was trained fine. But to actually quantify the quality of our model predictions, we developed a small website service for manual image labeling. And we cannot manually label 130,000 something images, but we can manually label around 600. That was quite quickly. And this is these were the random images. So this is the distribution of morphological classes that we get from manual image labeling. And we used these 600 images from the Astrogeo dataset as our validational for validation, essentially. And this is what we get as our result. So we can see that the results on real data are a little bit worse, lightly saying that on the synthetic data. So it's a little bit better than baseline, but still we can see that our trained model is predicting quite well the Gaussian sources and the single-sided jet sources, but not always. Some of them become Gaussian sources as well, and it isn't great at predicting double Gaussian sources or double-sided jet sources. So all in all, what we have done, we pre-processed and cleaned up the 130,000 Astrogeo images. We filled in 2 SQL tables with some meta parameters that could be used later. And we generated a synthetic image dataset as a training dataset. We obviously developed a CNN model and trained it on our synthetic images. And we got some sort of classification of these 130,000 Astrogeo images, which is already something. But due to, testing it on the validation data set that we actually manually labeled, we can see that these predictions could be improved drastically, probably. And we also created this web interface that probably will be later on modified somehow and probably could be used some for public service as well. So our future plans. Obviously, we would like to improve our quality of image predictions. And we also consider to investigate other machine learning algorithms, because drawing synthetic models is not ideal, and probably but we still would like to finish like a proof of concept with this pipeline. But we also can consider using conditional variation autoencoders to produce this synthetic images. And ideally, we would like to make a wrapper on this model and create a search tool for jets with similar morphology that all scientists could use, just uploading an image of a jet or any object and get however many similar morphology objects. We also considered to use the Blanford-Koenigsegg analytical model of jets to create for more physical creation of our synthetic images. Well, as a like really future plan is to try and adapt our model that was trained on parsec scales to kiloparsec scales, and maybe try and figure out the evolution from parsec scales to kiloparsec scales, so also with time. So yeah, this is it. I'm ready to answer any questions if there are any.
Thank you, Dimitri. Dimitri, I want to make sure, can you hear me?
Yeah, I can hear it, but
Okay, because I was going to interrupt you earlier. Any questions for Dimitri from the audience? I have a couple actually. So the first one has to do with you know, did I understand correctly that your original results where you were getting an almost perfect you know, classification metrics, were those based only on applying the convolutional neural network to simulated data alone? Have you, whereas, you know, when you apply it to actual data, you had a not so well, not so perfect behavior. Is that perhaps because your training, your simulated set of Gaussians, et cetera, might not be representative of where we're actually seeing in the data?
can you please rephrase your question again, because I got lost a little bit in the middle of it?
Is the simulated data that on which you've trained the network, is that representative of the actual morphological shapes that you see in the data? And if not, would that be an explanation as to why you're not getting the same performance of the convolutional neural net when you apply it on the real data?
Okay, so it is it's hard to tell, because it's well, I would simply answer that question if it was actually working, but right now, due to the fact that it's working not so well, it's I have looked through the Astrogeo dataset, well, not through it all, but for a lot of images, and I would say, at least for now, I think they're still representative, but the synthetic data should be still improved, and they should be not viewed as like visually they're obviously similar, but not to the neural network. So I would probably assume there is some additional moments and modifications that should be done statistically, and making images not only visually similar, but also like so the neural network will consider them also similar. So that's the main actually issue of this pipeline. So I'm still working on it.
Okay, yes, Cecilia?
Yes, one of the things you said is that you need label data because you're using a CNN, right? But I was wondering if you tried, or you think it could work if you try an architecture that could actually do unsupervised learning with CNN, like an autoencoder, for example.
I'm really hard to hear.
Okay, sorry, I'll go closer to the. Is this better?
Yeah, this is better.
Okay, so here's the mic, I guess. Yeah, I was wondering if it would make sense to try something like an autoencoder that is unsupervised.
Yeah, we considered that, but we initially would like to finish with this as a proof of concept and then probably use a autoencoder. Yeah, that'll be probably worked on in the future. Yeah.
Thanks.
One question I have for you, Dimitri, or anyone here working on radio dataset is, I mean, your inputs to your neural network is actually the images after you've done the cleaning aspect of it. And I understand, of course, that's making a lot of assumptions. I don't really remember how the clean algorithm works, but it's basically transforming UV visibilities into an image. Do you see a path forward if you were going to input, the data before you have done any cleaning? In other words, is the information that you need to perform this classification already included in UV data, or do you see the cleaning step as a necessary, step in order to perform the classification?
So we were going after a more or less simple CNN model for now, but we also will, we also consider the fact that we'll probably add not only the clean image, but also the UV, the visibility functions as additional input to our neural network. So it will essentially replicate the point spread function of the telescope, like the convolutional step.
Okay. Anyone else has comments on that? Anyone with experience here on radio data? I mean, is when you're going to perform morphological classification of images generated from visibility data and interferometry, is the information already there in order to perform these tasks, or is forming the image part of the process that you need to perform before it can be actually used for this downstream task? Yes.
Yeah, I mean, the similar research that the information is absolutely already there. And in fact, you're making a lot of assumptions about the structure when you image it. So you could potentially add even more nozzles to term, so to speak, as far as like large scale versus small scale emission.
Thank you. Okay, any other comments, questions for Dimitri? Okay, if not, please, if you haven't done it, please sign your name on the sheet down there, so please control who attends these talks. Dimitri, let's thank Dimitri again. Thank you so much for your talk.
Thank you for this opportunity. Thank you for having me.
Thank you so much.